Another relationship that is sometimes helpful to have is the relationship between the Euler axis and the quaternion. Now remember, the quaternion we actually developed from the Euler axis, and so previously we talked about the definition of the quaternion, which is E naught, Ex, Ey, and Ez is equal to cosine of theta. This is a capital theta over 2. Remember, that's the angle that we're rotating about the Euler axis. And then Ex times sine of theta over 2, Ey sine of theta over 2, and Ez sine of theta over 2. Okay, so that's the definition that we discussed previously in the development of the quaternion. So that should look familiar. But, and remember, Ex, Ey, and Ez are the actual components of the Euler axis itself. So again, if we draw this coordinate system over here of X, Y, and Z, there's some Euler axis here that has components Ex, Ey, and Ez, and then the theta is the rotation about that axis. So that's theta, and then we've got this Ex, Ey, and Ez. Okay, so this is the Euler axis definition that then we used this change of variables defined here to come up with a quaternion definition where we have a scalar and then 3 components that are vector components within that quaternion. Okay, so if we have an Euler axis, we already know how to get the quaternion just from this relationship here, but we can actually just flip this and solve for theta, capital theta, Ex, Ey, and Ez as a function of the Euler angle, or excuse me, as a function of the quaternion, if we like. So that's pretty straightforward. What we get is that theta, Ex, Ey, and Ez. Again, if you just solve each of those equations here, what we get is that theta equals 2 cosine minus 1 of arc cosine of E naught. And then capital Ex is equal to little ex divided by the sine of theta over 2. Ey divided by sine of theta over 2, and little Ez over sine of theta over 2. Okay, so that's pretty straightforward. We just get that by rearranging this equation to solve for theta, Ex, Ey, and Ez as a function of the quaternion components here. So yeah, again, this can be helpful, especially if you're trying to visualize the Euler axis during flight or during some maneuver to visualize the orientation here. You could actually put you could solve for this Euler axis and rotation angle, and somehow in a graphical display show what this Euler axis looks like relative to the aircraft. Remember, these components, Ex, Ey, and Ez, have the same components in the Earth fixed coordinate system as they do in the body fixed coordinate system. And so you could actually show this vector relative to the aircraft itself during a simulation to show where the Euler axis is based off of the orientation of the aircraft.